right, so last time we talked about ions and ionic compounds. We've talked about covalent bonds. And one of the things we've talked about in particular with covalent bonds has been the electronegativity difference. Okay, so we said electronegativity difference, which is that delta En value that we've looked at in the past, right, is just calculated from the electronegativity of one element, or so atom A, minus the electronegativity of atom B. And from those values, we have a range for electronegativity differences. That range can be anywhere from 0 all the way up. It's actually not as high as 4. It's actually more like from 0 to 3.28. And so that would be based on, if we look at our electronegativities of the elements of fluorine, which is 3.98, and francium, which is the smallest value at 0.7. If you look at those electronegativities, you'd really come up with a value for that of 3.98 minus 0.7, so you get 3.28. So that's really sort of the spectrum of possible electronegativity differences between bonded atoms. Now, we sort of assign some arbitrary cutoffs to this, saying, well, if you have a value that's between 0 and 0.4, so in this range, between 0 and 0.4, that electronegativity difference is so small as to essentially mean that those electrons are shared equally or nearly equally, enough to allow us to say that, well, if the electrons are shared equally, that's going to be a non-polar bond, right? A non-polar and covalent bond. So that's a key here, okay? But as that value gets larger, you start to share electrons less evenly. So you start to bring in this partial negative character to one of the atoms and partial positive character to the other atoms, as the electrons, right, spend more time over on the more electronegative element. And so our arbitrary cutoffs for this range fall between 0.4 and about 2 for the electronegativity difference. Now, again, these are arbitrary cutoffs. Some people may talk about them in a different way, but between 0.4 and 2 is when you're going to wind up having a polar covalent bond. The polarity comes about because of that uneven sharing of those electrons, okay? Beyond 2, from 2 to, as this one says, 4, really it's 2 to 3.28, those two elements are sharing the electrons so unequally as to consider them to have essentially transferred an electron entirely. And that's where we get an ionic bond, right? And so that's going to be something you'll find primarily, or really only, with metals and nonmetals. And the reason you're going to have metals and nonmetals is because really the most electronegative elements are the nonmetals. And so those really stand out as being very electronegative. And so those are going to have to be part of these ionic bonds. But in this range of, for the polar covalent bonds, is when you're going to start to look at and start to see covalent bonds where the electrons are shared unevenly. And really it's just a matter of understanding now that there's a spectrum here. There's not just polar, nonpolar. There's really polar, nonpolar, ionic, and within the nonpolar and polar compounds, it's basically because you have a smaller electronegativity difference, and in particular within the polar covalent compounds. In those polar covalent compounds, there's the spectrum of polarity, where the bigger the electronegativity difference, the more polar it is. And so you can look at this as also being sort of over on, toward the right side. As you get electronegativity differences that are larger, we can say that those are more ionic in character, right? And those electronegativity differences, when they're smaller, that's going to be less ionic in character. Right? If it's less ionic, it's more covalent, more equally shared electron density. And so we can get some examples of this. You can see that if we just take some examples, you'd have something like a carbon hydrogen bond, right? That electronegativity difference will just be 2.55 minus 2.20. So you're going to get a value of 0.35. And so we can say that is a nonpolar covalent molecule, or bond, I should say. Okay. If, however, you have something like OH, okay, so the electronegativity difference there is going to be 3.44 minus 2.20. And so that one will be a difference of 1.24. That's going to be considered polar equivalent. Okay. And then you can look at something like, let's say sodium fluoride, where you're going to have an electronegativity difference of 3.98 minus 0.93. So you're going to get a big electronegativity difference there, right? So that would be 3.05. And so that one would just be ionic. And you could do this in this for any of the elements in the periodic table. So to give you an idea of the range, when would you have a zero? So a carbon-carbon bond would have an electronegativity difference of 2.55 minus 2.55, right? And so that would be zero, right? And so that's very much covalent, right? Nonpolar. And the biggest difference you could have is the francium fluoride, right, which will have an electronegativity difference of 3.98 minus 0.7. So you're looking at 3.28, so that's ionic. Okay, and so you're really just looking at those electronegativity values, right? This delta En, being able to calculate those values is of utmost importance when you're looking at the polarity. And as we start to get into drawing more molecules, that's going to be more important, because you're going to have to take that electronegativity difference for each of the bonds in a molecule to see if there's a dipole. Okay, so that's sort of the idea of the spectrum of electronegativity differences. And before we start to draw out molecules, there's one other thing we want to model within molecules, and that's the energy associated with bonds. Okay, so the average bond energy, okay, is an important thing for us to understand and be able to use to estimate the energy it takes or that's either produced or needed for a chemical reaction. If you actually take the average bond energy for a given bond, it's just an estimate of the energy it takes to break a bond. Remember, it's if we're breaking a bond, we're going to put energy in, and so that's going to have a positive value. And so there are some trends here, and there's some tables. You'll notice on this page we have a table for bond lengths and bond energies. We'll talk about those in a second. Here, there's another table. The units are a little different. This has more of them in this, and we'll talk about this table as we do a chemical reaction. But there's some things to note here for these average bond energies, right? When we say it's the average bond energy, okay, that's a key here, right? It's the average across many, many, many chemical compounds, okay? And these are experimentally determined values that we can use as our estimate to estimate for a chemical reaction, the energy or the enthalpy of that reaction, right? Okay, so that's one thing. Another thing to note here is if we look at and start comparing, and we can compare, actually we'll compare these three. I think this is sort of the apt comparison. We have three bonds, right? We have a single bond, In this case, we're going to look at the carbon-carbon bonds. We have a double bond, and we have a triple bond. Okay, and a single bond, that's one shared pair of electrons. So we can say shared electron pairs. Right? In a single bond, there's one shared pair of electrons. That's why there's one line written here. Okay. If you only have the one line there, right, that's a single bond. If, however, you have two lines, like in a double bond, the CC double bond, right? And so our single bond is just represented by that. The CC double bond is represented by two lines, so that's two shared pairs of electrons. And the CC triple bond is three lines, and so that's three shared pairs of electrons. Now, if you're sharing more pairs of electrons, you would imagine that as you share more pairs of electrons, the bond's energy, right? So as you say more shared pairs of electrons, you would expect the bond energy to increase. And if we come over to this other side, right over here, we have our bond energies, right? And sure enough, as you go from a single bond to a double bond, you'll notice that the bond energies, they don't quite double there. And when you go from to the triple bond, it's not quite triple the energy of a single bond, but it is definitely a significant increase in the bond energy. In other words, it takes more energy to break a triple bond. Right, than it does to break a single bond or a double bond. Okay, so that's a key there. So the bond energy, the amount of energy it takes to break a bond, increases as you start to go from single bonds to double bonds to triple bonds. And at the same time, if you look in the middle here, we have the average bond length. And so as the average bond energy goes up, the average bond length decreases. Basically, they're closer together, which means they're pulling on the electrons a little bit more strongly because of the proximity of the nucleus to those negative charges. So as the bond energy increases, the bond length decreases. At least when you're comparing apples to apples, right? All of these carbon-carbon, single bonds, double bonds, and triple bonds. And the same trend would go if you start to look at the nitrogen bonds, right? Nitrogen single bond is much lower in energy than the nitrogen triple bond. In the case of the single bond compared to the triple bond for nitrogen, the triple bond is significantly stronger, right? That's 6 times almost the strength of the single bond, right? So there's a big difference there. And so it's going to depend on the elements that are involved in those single, double, and triple bonds, how strong those are and the trend in that strength increase. Well, and for nitrogen, we're going to see, well, basically you can think about nitrogen as being really, really, really stable as far as nitrogen gas, because of that triple bond. And that's evident because most of the air, right, 78% of the air that we breathe is nitrogen, and it's not really reacting with us. So it's nice that it's stable, because if it wasn't stable, it might react with us, and that can cause some other problems. And so that's one of the things to look at, is sort of these average bond energies, and as being the amount of energy it takes to break a bond. Now that's an important thing, because when we break a bond, it takes energy. But when you make a bond, energy is going to be released. And so when the amount of energy is released is going to be excuse me, equal in magnitude, but opposite in sign, right? The energy is going to be released. Hold on, someone's not muted there. Okay, right. So when the energy is released, so energy is released when you form a bond. So you can think about it as there's a positive value for the energy when you break a bond because you're putting energy in. When you make a new bond, you get energy out. So you're going to subtract off essentially any energies from the bonds you make. And we can use that as a way of estimating the energy in a chemical reaction. And that's the next step that we're going to go to after looking at this table. So a couple things about this table. The upper portion of this table, so these are average bond energies in terms of kilojoules per mole. And then there's also the bond lengths, and those bond lengths are in picometers. So if we look at the table here, we were looking at, again, bond lengths were in picometers, but the average energy here is in attojoules. So this is for one bond in this table. Okay. In this table here, it's per mole, right? And so this table is going to be more useful to applying these average bond energies to things like chemical reactions, right? Because our chemical reactions are written in such a way that we can say, well, in this particular example, 1 mole of methane plus 2 moles of oxygen react to form 1 mole of carbon dioxide and 2 moles of water, right? And so the phrasing of that is important. This table in the upper portion has all single bonds, right? And so they're grouped together such that you have hydrogen, carbon, nitrogen, oxygen, right? But you'll find, of course, the carbon-nitrogen bond is here because carbon comes first in this, right, et cetera, right? So this is for a lot of the single bonds that are out there. By no means is this all of the bonds, right? This is only a handful of the elements that we're going to look at. But it's a pretty good table that has a lot of the elements that you'll see regularly, in particular in organic compounds, because there's a lot of carbon, right? There's a lot of hydrogen, carbon, nitrogen, and oxygen, right? These are the 4 main elements that you're going to see in most organic compounds, though you will occasionally see some silicon, and phosphorus is one that you're going to see more often than silicon really in a lot of organic stuff. Which is, of course, what makes up the biological molecules that we deal with, right? So sulfur you'll find there as well. On the bottom, you'll notice there's a set of bond energies for multiple bonds, okay? Now, something to notice here is here's where you have the bond energies for the CO double bond. So if you actually look at this, there's 2 values here. There's sort of a generic CO double bond, and then it tells you separately in CO2, each double bond, right? This is each CO double bond. Each one is a little bit stronger than a typical CO. So where might we have those? Well, CO2, you'll have C double bond O, C double bond O. There are 2 of them, right? Each of those double bonds, right, will be 799 kilojoules per mole. Right, for both of them. But you have other types of CO double bonds. You might have CH2O, okay, which would be C with a double bond O and an H and an H. And that one would be where you'd have your 745. Okay, so this here with the carbon or the carbon-oxygen double bond and carbon dioxide, each of those is a bit stronger, and that's good because, well, carbon dioxide is a fairly stable molecule as well, right? And that's also one that's in a significant enough composition of the atmosphere that it's a good thing that it's stable. You'll notice that the other thing that's sort of weird down here is that O2, so the oxygen molecule, is just written as O2. And there's a reason for it, and we're going to discuss this more a little bit later, but I'll sort of line it up here for you, is the oxygen, so the O2 molecule, you can draw it in a couple of ways. As we're going to see a little bit later, to draw the O2 molecule, you can draw it doing a Lewis structure, and that Lewis structure is going to be represented like it's seen here. And again, we're going to get more into these Lewis structures in a little bit, but that's a way of drawing it. But experimentally, we know that this is not how oxygen exists in the real world. And we'll talk more about that later in this chapter and in the next chapter. Okay. Not how oxygen actually exists. And in order to understand that, we have to look into how the oxygen atoms are bonded to each other. And so there's a bit to this. So the Lewis structures that we'll see in a little bit are going to be good ways of representing molecules, but they're not perfect. They're really good for certain things, whereas other representations are better for other things. So with this particular chemical reaction that we have in the top, we can use this table to predict what is the average, or what is the enthalpy of this reaction. So what we need for this, as we go to predict the enthalpy of this reaction, we can say, well, what is the average bond energy for this chemical reaction? Okay. And so one thing we want to do here is we're going to learn how to draw Lewis structures later. I'm going to draw them here for you to give you an idea of how our representations of molecules will be of use as we start to look at the energies of reactions. So what I've just drawn on this screen just below the methane molecule is the Lewis structure for methane. Okay, so what you'll know is that in each methane molecule, there are 4 CH bonds, okay, in one molecule. Okay, or you could say, well, there are 4 CH bonds per molecule. There will be 4 moles of CH per mole of that molecule, okay? So that's a thing that's important for us to know too. With O2, like we said above here, right, on this side, we're only going to deal with O2 as O2. Okay, and so that'll be something that's useful for us going forward. So we're just going to say, okay, so we have an O2 molecule and we have another O2 molecule, which gives us essentially 2 moles of O2 in this chemical reaction. For carbon dioxide, the Lewis structure looks like this. And so what you have here is 2 moles of C double bond O, and sort of parenthetically in CO2, because we're going to use that CO double bond for the CO2 specifically if we ever see that in our table. And then finally, we've got 2 water molecules, which means we have a water molecule there and a water molecule there. If I'm drawing out the proper Lewis structures, I need to put in my my electrons, which again, we'll talk about shortly. But what you can see here from drawing out these molecules, you can see that there are 4 OH bonds. Or excuse me, I should say 4 moles of OH bonds. And so understanding that is first and foremost. How many of the different bonds are we looking at here? And the strategy for figuring out what is the enthalpy of the reaction is we're going to break all of those bonds that are on the reactant side. Okay, and we're going to form all the bonds on the product side. Okay, so that's the strategy. We're going to break all the bonds and then we're going to form them. So our assumption is that we're splitting all of these molecules into their component atoms and then we're putting them all back together as products. Well, that's not actually how a chemical reaction occurs, but it is a way of modeling how much energy changes place from reactants to products. It may not be perfect, but it's a way to do it that has some benefits. And the benefits are here that we can really use these average bond energies to estimate all kinds of different potential enthalpies of reactions. And so what we need to do here is go to the methane, which is start out with CH4, which means we have CH bonds. So we're going to come up to our table and we're going to find the CH bond in the table. And we're going to look at the energy there. It says that it's 413 kilojoules per mole. Okay, so the CH is 413 kilojoules per mole. For oxygen, we're going to come back up here. So our oxygen is down on the bottom. We looked at that before. It's 498 kilojoules. Okay. So our oxygen is 498 kilojoules per mole. Okay. We can go to our CO double bond. Right, remember this is in CO2. So we go back up here and we use the value here for CO2, 799 kilojoules per mole, because that's our molecule that we're dealing with. So we can plug in here 799 kilojoules per mole. If this was a CO double bond in another compound, we would have used the 745 value. And then our other bond is the OH bond. And so we go to our table and we find our OH bond here is 467 kilojoules per mole. Okay. And now we can put it into a chemical equation. So basically, for finding the delta H of the reaction, that's going to equal the sum of the enthalpies of the average bond energies of the bonds broken minus, and this is when we form the bond, minus the sum of the average bond energies of the bonds formed. Okay. And so to figure that out, all we have to do is we go up here, we say, oh, okay, well, we have 4 moles of methane. Excuse me, 4 moles of CH bonds in methane. Times 413 kilojoules per mole of those CH bonds plus oxygen. So here we have 2 moles of O2 times 498 kilojoules per mole of O2 minus 2 moles of C double bond O at 799 kilojoules per mole of CO plus 4 moles of OH times 467 kilojoules per mole of OH. Okay, and we just do the math from there. It should be fairly straightforward. So this would be 1652 kilojoules, right? Because our moles of CH and moles of CH are going to cancel. Our moles of O2 and moles of O2 cancel. So we're going to have 996 kilojoules minus here moles of CO and moles of CO cancel. And so we have 1598 kilojoules plus the 4 moles of OH would be 1868 kilojoules, right there. Okay, and if we do the math on this and add up those values, you would find the delta H of the reaction is going to be negative 818 kilojoules for the chemical reaction as written above. And so this should make some sense, right? It's exothermic, right? It's a negative value here, which makes sense because this is a combustion reaction for methane. So you're burning methane gas, you're putting out, for every mole of methane gas that's burned, it's producing 818 kilojoules, right? Or giving off 818 kilojoules of energy, okay? And so this is what allows us to predict the energy associated, the enthalpy associated with a chemical reaction, the heat that's associated when bonds are made and bonds are formed in a chemical reaction. And so that's one way of modeling and estimating energies for chemical reactions. But one of the things that you need as a skill to do this is you'll need to make Lewis structures for the molecules that you'll be working with. Okay. And as we jump into that, the thing we need to understand for the next bit of this and for making Lewis structures is the idea of the localized bonding model. Okay, so the localized bonding model is a key for, and we've been using this a little bit, right? We've said that when we've had a molecule, say the hydrogen molecule, so we'll start out with H2. Well, each hydrogen atom has one proton and one electron, and the protons and the electrons, right, are shared between the two molecules. That's why we write out a H2 molecule when we draw it structurally like that, with the lone pair, or a pair of electrons, not a lone pair, but a pair of electrons in between the two hydrogens. And that is what's known as a bonding pair. Okay, and so that's a bonding pair. Now, when we're doing this, we're really interested in only the valence electrons. The core electrons are not going to be involved in the bonding. Okay, so a bonding pair is just a pair of electrons that's being shared. Okay. Okay, but you'll also encounter what are called lone pairs. And so our other molecule that we have here is the oxygen molecule. And what you'll see is for the oxygen molecule has two OH bonds, whereby the hydrogen and oxygen are sharing a pair of electrons. You have these two electrons in the middle, those are core. So they're not going to be involved in the bonding. But there are two other electrons on oxygen, or two other pairs of electrons on oxygen that are written here. Those are going to be what are called lone pairs. Okay, so when we draw a Lewis structure in particular, right, a Lewis structure for water will be written like so. And so you'll have two lone pairs, right? That's how we're depicting those lone pairs, okay? Now, those are electrons that are not involved in the bond, okay? So not bonded, okay? But when we look at the the localized electron bonding model, we're saying that the electrons are going to either reside in lone pairs, okay? And they're going to sit essentially in an orbital on that oxygen atom as a lone pair, or a pair of electrons sitting in that orbital. Or we're going to have bonded pairs, and bonded pairs are shared, right? So those bonding pairs are shared electrons that are that reside between the two atoms, right, or are localized right between the bonded atoms. Okay, and so in other words, that's where you would find them. You'd find them in between those two atoms, and that'll have implications down the road when we start looking at VSEPR model, where those electron pairs in bonds or electron pairs in lone pairs are going to repel each other to give us shapes of molecules. And those shapes of molecules will be important for three-dimensional structures and reactivities of molecules moving forward. Okay. So this localized electron bonding model is what we're going to use as we start to get into Lewis structures. Okay. So a couple of things in Lewis structures before we start to draw them all out. So Lewis structures are a way of depicting molecules that will give us some useful information in and atoms for that matter. What we're going to depict is, first and foremost, we're going to depict using the atomic symbol. Okay, the atomic symbol will depict the core electrons and the nucleus. And that's basically everything that is not involved in bonding. It's held in very, very tightly, so you don't have to draw them, you don't have to depict them because they're not going to interact with other things. Okay. Then you'll have dots, and dots are going to represent valence electrons. Okay, and you'll have lines. And like we've used in the past for lines, when we've looked at structure, lines are going to represent a pair of bonding electrons. And so the first thing we need to do is start to depict some atoms. Okay, so when we look at an atom, something like the hydrogen atom has one electron. So you will write the hydrogen in there. That covers, well, there aren't any core electrons in hydrogen, but there is a nucleus. And so we have hydrogen, and we can draw a dot next to it. Now we're going to draw these dots, these valence electrons, on any of the four sides. Now, the first one that you place, it doesn't really matter which side you place it, as long as there's a dot on hydrogen representing its valence electron. The second element, helium, is going to have two dots. Okay. Now, if you're depicting helium properly, you're going to put those two dots on the same side, and this is sort of the one time you're going to do that. The only time you're really going to do that is you're going to put those two dots on the same side for helium, because those two electrons are in the same orbital. And that's a key here, is that the dots in the same orbital are going to be on the same side. And we know they're in the same orbital because we know that helium's electron configuration is just 1s2. So there's helium. We then go to the next period, right? You run into lithium. Now remember, lithium is going to have 3 electrons total, but 2 of those electrons are the same as the helium core, right? They're the helium core electrons. So we're not going to depict those core electrons in the 1s orbital. We'll only depict the electron in the 2s orbital. So there's only one dot on lithium. Then we go to beryllium. Now, starting with beryllium, what we're going to do is split up the electrons as we place them around, because something about molecules, we know molecules will tend to form bonds or become ions such that they either increase the number of electrons up to 8, what we call an octet, which completes the noble gas electron configuration. More on the octet later. Or they're going to lose electrons in order to go down to the electron configuration of the element, the noble gas in the row above. And so what we're going to start to do here is, as we place electrons around an atom, we're going to split them up. Now you could put them on, they must be on different sides. So remember, right, left, bottom, or top. And I generally write them on opposite sides for beryllium, but that's sort of a personal preference. That's something that'll come later. You'll see why I do that later. Now, the reason that you put them on different sides is because those electrons will be used in bonds. And so putting them on different sides depicts, well, this is a single electron that is available for sharing. Okay. So if we go to boron, so boron's electron configuration is 1s2, 2s2, 2p6, which means it has 3 valence electrons. So we can put our 3 valence electrons around, starting 1, 2, 3 valence electrons on boron. Okay. Next we have carbon. Carbon is 1s2, 2s2, 2p2. And so there are 4, right? The 2s2 and the 2p2, there are 4 valence electrons. So here, go 1, 2, 3, 4. Okay. Then we go to nitrogen. Nitrogen has 5 valence electrons. So we place 1, 2, 3, 4. And then our 5th electron will pair up with one of the other electrons. Okay. And so something about each of these Lewis diagrams or these Lewis structures for the atoms is going to tell us how many bonds that element will make. And I'll get back to that in a second. Then we've got oxygen. Okay, so oxygen has 6 valence electrons. So we go 1, 2, 3, 4, 5, 6. Okay, and again, you could pair them up on the same side or different side, doesn't really matter. Something about Lewis structures is they do not show the actual three-dimensional structure of a molecule or an atom. So then we've got fluorine. Fluorine will have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Now, how do you know the number of valence electrons? If you go back to your electron configurations, remember valence electrons are the ones in the outer shell, okay? And when we look at those valence electrons, we can count them fairly easily, right? The oxygen has an electron configuration of 1s2, 2s2, 2p4. And so the 2s2 and 2p4, the 4 2p electrons, right? So 2 s electrons and 4 p electrons gives you a total of 6 electrons in oxygen's valence shell. And finally, we've got neon, which is the noble gas. That's 1s2, 2s2, 2p6. So the 2 s electrons and 6 p electrons means there are 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8 electrons around that atom, okay? Now, in the Lewis diagram of the atom, the number of unpaired electrons okay? So those would be like that, right? Like that, and that, or that, that, and that, right? Those are all the unpaired electrons, right? The number of unpaired electrons dictates the number of bonds an element will form. Okay, now more on this later. There are going to be exceptions that we'll see in the future. Okay, we'll see those as we discuss the exceptions to what's known as the octet rule once we start doing these Lewis structures. Okay, so that's electrons around atoms. Okay, placing electrons around atoms is pretty straightforward, pretty simple. Now, if we want to look at ions, we're going to pick some elements. So we're going to take an element. We're going to depict, so I would say element or ion. Okay, and we'll do the Lewis structure of that element or ion. Okay. So there's the Lewis structure. We'll do the Lewis structure of a couple of them. So we'll do, really I'll do 2 examples here so you can see how these go. We'll do, the first we're going to start with a cation and then we'll go to an anion. And then we'll put these together in a little bit as a compound. Okay. So when we look at the first ion or element that we're going to look at is sodium. So sodium is in the first group, right? Its electron configuration is 1s2, 2s2, 2p6, 3s1. And so the sodium, the sodium atomic symbol represents the core. So it's the 2s electrons, the 2p electrons, the 1s electrons, and the nucleus. And then there's one dot on sodium because there's 1 electron in the 3s orbital. Now, if we look at the ion that sodium forms, it's Na+. And so what you do there is you draw in the element or atomic symbol, you write down the charge, and in this particular example, right, the sodium ion Lewis structure is the same as what we've been depicting for sodium. You don't have to write in the electron because that electron is gone, right? right? It's lost that 3s electron, the only one that it had in its valence shell. So sodium went from 1 valence electron as an atom to 0 valence electrons as an ion, okay? Our example of an anion will be chlorine. It'll have a Lewis structure, Cl, so its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p5. So you look at the 2 3s electrons and the 5 3p electrons for a total of 7 valence electrons. And you can actually count these by looking at the group that it's in. So group 17 or 7a, depending upon the periodic table, group 17 will have 7 valence electrons. So here we have to put 7. So 1, 2, 3, 4, 5, 6, and 7 valence electrons. But we know that chlorine forms Cl minus, and so if we look at this structure, it'll be the chlorine. If it's gained an electron, remember when we go from Cl to Cl minus, it gains an electron, right? And so now we have 8 valence electrons to place. So we go 1, 2, 3, 4, 5, 6, 7, and 8. And of course we have to put in its minus charge, okay? Now when we, and so that depicts the Lewis structure for a chloride ion. So we don't, when we're doing chemical formulas and the formula of the ion in, say, a total ionic equation, we don't depict all the electrons, we just depict the charge. But in a Lewis structure of that ion, you do depict the electrons. And so if you're looking at the compound sodium chloride, right, if we're really looking at this from a Lewis structure standpoint, we've got sodium, and you can put the chloride in brackets there, just to sort of show that the electrons are all on that chloride ion, okay? And so that's how you depict atoms versus ions when you're doing Lewis structures. Now, most of the time, we're not going to depict ionic substances doing Lewis structures because we know that the Lewis structure doesn't really make sense for an ion in the same way that it will for a covalent molecule, because remember, the ions just form these tightly packed ionic substances where the attractions between these ions are what hold them together. So we're not looking, when we look at an ionic substance, we're not really looking at it from a standpoint of bonds, we're just looking at it as far as the ions are held together. But when we have a molecule, now we have to start to depict the bonds that are holding the atoms together within a given molecule. And so to do that, we have a set of rules, okay? So I'm gonna walk you through these rules, and we'll go through and utilize these rules as we draw in various different Lewis structures. And we're gonna start with some simple Lewis structures and that don't need all of these rules, and then we'll get increasingly more complex as we proceed through our drawings, right? So we're gonna start simple and get more complex. So the rules for making Lewis structures are as follows. We're gonna add the total number of valence electrons in the molecule that we're given, okay? And to do that, really all you have to do, add up the group numbers of all the atoms in the molecule. When we say group numbers, we're talking, right, 7A, right, 3A. When we look at this, 17, depending upon your periodic table, would give you 7 valence electrons. Okay, so you add up the group numbers, assuming you're not taking into account the transition metals, because with the transition metals, you can deal with transition metals when you get on into 102. Okay, so you're going to add up the group numbers of all the atoms, and that'll be the total number of atoms in the molecule, unless it's an anion or a cation. If it's an anion, you're going to add 1. Right, electron, because, or if the charge is -1, if the charge is -2, you're going to add 2 electrons, right? If it's a cation, you're going to subtract the number of electrons equal to the charge, right? So if you have a -1, you add 1 electron. If it's a -2, you add 2 electrons. If it's a -3, you add 3 electrons, etc. If it's a +1, you remove 1 electron. If it's a +2, you remove 2 electrons. If it's a +3, you remove 3 electrons, etc. Okay, that's the first thing. So we add up the total number of valence electrons. Then we're going to draw in the central atom and the surrounding atoms, okay? So the central atom, generally, not always, but generally that central atom is the one that has the most unpaired electrons in the Lewis diagram for that element. So if we go here, what I'm talking about for that central atom is all of these atoms, okay? So it's the number of unpaired electrons. The more unpaired electrons that atom has, the more bonds it can make, and that's why it would want to be the one in the center, so it can form more bonds to those surrounding atoms. And so you'll put that central atom, once you've identified it, you'll put the central atom in the middle and the surrounding atoms outside. Okay? If those central atoms have the same number of valence electrons, right, the central atom is usually the one with a smaller electronegativity. So you'll use the electronegativity table in doing this as well. The next thing you're going to do is you're going to draw a single bond between the central and the surrounding atoms. Okay, each bond will represent 2 bonding electrons. Okay, and so you're going to assign those 2 bonding electrons to each bond, and you're going to subtract the number of bonding electrons from the total number of valence electrons that you figured out in part 1. Once you've done that, you're going to see, are there remaining electrons? If there are remaining electrons, we're going to assign the remaining electrons first, and we're going to start by placing those remaining electrons on the more electronegative elements until an octet is reached, okay? So an octet, so that leads us to the octet rule, all right? The octet rule says that elements will form covalent bonds such that 8 electrons will fill the covalent, or will fill the valence shell. So you want essentially 8 electrons to surround a given atom in a Lewis structure. And so first you place any remaining electrons. Now there are going to be some exceptions. You'll notice that we have except helium, beryllium, boron, aluminum. There's some others. We'll talk about those later. Okay, for now, we're going to assign the remaining electrons as lone pairs to give octets. If an atom doesn't have an octet at that point, and remember, we're filling electrons first in the elements that are more electronegative, because the more electronegative elements are the ones that are going to want the electrons more, and then we can move them around afterwards if some atoms don't have octets. Okay, if we do that, we're going to take a lone pair of electrons from one of the bonded atoms and form a multiple bond with that element that doesn't have the octet, thus increasing the number of electrons that surround it. Right? So it'll go from a single bond to a double bond, which means it'll be sharing more electrons. Okay. Then, after we get good at doing this stuff, we're going to do this other thing, and that is determining the formal charges of the atoms. So formal charges are basically, when you consider an element in a compound, the formal charge tells you, well, how many electrons are there in the element in its free state when you just have an atom of that element, as compared to how many electrons surround it when it's in a molecule. And the way you're going to do that is you're going to do a calculation. And that calculation is something we'll look at a little bit later, but basically you're going to take the number of valence electrons of that atom in its free state, subtract off the number of lone pair electrons and half of the number of bonding electrons that are attached to that. And so that'll give us this formal charge. And formal charges, basically atoms want to have 0 charge if they can. They still want the octet, but overall they want a 0 formal charge. And so this formal charge is going to be a way of allowing us to determine the stability of one structure versus another structure, assuming we have more than one Lewis structure for a given molecule. So now we're going to get a bit of practice, and you have a lab coming up where you'll get even more practice on this stuff. I believe that's the one you're going to do on Tuesday of next week. So you'll get a little bit of practice before we get there. Here we go. So I actually have some of those things that we just talked about over here. Right? Each element forms covalent bonds such that 8 electrons occupy its outer shell or its valence shell. Right? To calculate the formal charge, and of course there's a spelling error there, I'll go fix that later. The formal charge on an atom in a Lewis formula is equal to the total number of electrons in the free atom minus the number of lone pair electrons minus 1/2 of the total number of shared electrons, or another way to look at that is bonding electrons. Okay. When you have molecules with more than one possible structure, right, and we say more than one possible structure, we're talking about the structure will satisfy the drawing rules that we talked about up here. It's possible to have more than one structure that'll satisfy that. And so you want to do, in order to identify the correct structure, right? The correct structure is the most stable version. That's going to be first off the one with the smallest formal charges. So you want small numbers. You don't want +2 and -2 formal charges, because if you think about what a +2 and a -2 formal charge is, a +2 formal charge says a given atom with that +2 formal charge will have 2 fewer electrons than it really, really wants. Or a -2, it'll have 2 more electrons than it really wants. So that's going to be very rare when you're going to have +2s or -2s as formal charges. It might happen, but it's rare. Then the other thing beyond that is if there are negative formal charges, you want the negative formal charges to be on the more electronegative element, right? Because the more electronegative element is going to be the one that wants the electrons more. If you have a positive charge on any element, well, then you want the positive charge to be on the less electronegative element, because the more electronegative elements will want the electrons more, thus leaving that less electronegative element with a positive charge, okay? And so we're going to go through some examples. We'll talk about these. We'll go through the calculations as we move forward as well. But we're going to start simple. Now, one of the reasons that you need to have water's formula memorized and ammonia memorized and methane memorized is there are going to be a lot of times where we're going to use those as models for molecules in a number of different ways. One of the ways is, of course, with Lewis structures. We'll start to see some relationships between those 3 molecules, water, ammonia, and methane, as we proceed through the rest of this chapter. They're good things to compare, okay? So let's now put together the Lewis structure for water. The first thing is we want to add up the total number of valence electrons. So we have hydrogen, so it'll be 2 hydrogen atoms times 2 valence electrons, times, what am I doing? There's only 1 valence electron on hydrogen, So 2 hydrogen atoms times 1 valence electron. And then we have oxygen, which has 6 valence electrons for a total of, and so when you ever see this VE, that's valence electrons, okay? For a total of 8 valence electrons in this molecule. The next thing we're going to do is we're going to place the central and surrounding atoms. So I'm going to draw out my Lewis diagrams for the 2 types of atoms here. So oxygen, we said, has 6 valence electrons. So that, again, is what you're going to find out from the periodic table. Now, again, when you place these in the diagram, doesn't matter where they go specifically. Now, you can draw out the water is the central atom in the middle, because it has, notice, 2, I'll change my color here briefly. All right, water has 2 unpaired electrons, whereas hydrogen only has 1 unpaired electron. Okay, so we put our oxygen in the middle, and we surround it on any of those 4 sides. So I'm going to sort of do this, separately down here. Remember, Lewis structures are not showing you the shape of the molecule. all you're doing is looking for connectivity of atoms, right? What atoms are bonded to what atoms when you have a Lewis structure? So I'm going to sort of do these two Lewis structures simultaneously, okay? So we took and we did steps 1 and 2, right? 1 was adding up the total number of valence electrons. 2 is draw the central atom in the middle and the surrounding atoms around it. 3, we're going to draw bonds between the central and surrounding atoms. And then we're going to subtract the number of bonding electrons from the total number of valence electrons. So we go back to the water molecule. We draw a bond between each of those atoms. And those bonds, there are 2 bonds, right? So those are 4 bonding electrons. Right? So if you see a B E minus, that's bonding electrons. Okay, so we're going to subtract 4 bonding electrons, which will leave us with 4 valence electrons remaining. And then our next rule says we're going to complete our octets, right? That's rule number 4. Assign the remaining electrons as lone pairs, giving all octets to atoms except for hydrogen, beryllium, boron, aluminum. And so hydrogen is one of those special cases because it can only hold a total of 2 electrons around it, because its shell, right, is the 1s orbital. That's the only electrons in that first shell is in the 1s orbital. So here we have 4 electrons to place. So we place 1, 2, 3, 4. Okay, and I can do the same thing to this other version. 1, 2 bonds, subtract off your 4 bonding electrons, leaving you with 4 valence electrons, and we place them on oxygen first. And so what you have with hydrogen, hydrogen really wants a duet, right? If an octet is 8 electrons, a duet is 2 electrons, right? It just wants to fill its 2s orbital and it's happy, okay? And so that right there, so on this we don't have to do formal charges. We could calculate formal charges. So why don't we do that for the hydrogen and oxygen? So formal charges. Okay, so for hydrogen and oxygen, so hydrogen's formal charge is going to equal, okay, so the formal charge will equal the total number of valence electrons in the free atom. So for hydrogen, there's 1 valence electron in a hydrogen atom, minus the total number of lone pairs of lone pair electrons, not lone pairs of electrons, but lone pair electrons. So each lone pair counts as 2 in this calculation. But each hydrogen, notice if you look at this, there are no pairs of electrons on the hydrogen atom. So minus 0, minus, this is where we have 1/2, so go back up to the formula, right? 1/2 of the total number of shared electrons or bonding electrons. So if hydrogen has 1 bond to it, that means it's sharing 2 electrons. So 1/2 of 2. So the formal charge on hydrogen is equal to 0. 1 minus 0 minus 1/2 of 2 is 0. Now, if there's a formal charge of 0, you do not need to label the atom. Okay. Then we've got oxygen. So oxygen has a total of 6 valence electrons in its free atom, minus we have the total number of, right, if we go back up here, minus the total number of lone pair electrons. So we have 1, 2, 3, 4 lone pair electrons. So 6 minus 4 minus 1/2 of the total number of bonding or shared electrons. Each of the oxygen is sharing in 2 bonds a total of 4 electrons. So minus 1/2 of 4. Do that math. 6 minus 4 minus 1/2 of 4 is 0 also. So we don't have to label any of the atoms with their formal charge in either of these. Both of these would be correct Lewis structures. And the only way those differ is which side you put the hydrogens on. Those are the same. That doesn't tell you anything different. Those are the same molecule, the same structure. The Lewis structure really doesn't vary on these because we don't actually care which side these atoms are on in this circumstance, okay? Now, we can do the same thing for ammonia. So for ammonia, the number of valence electrons we get from hydrogen is, well, we have 3 hydrogens times 1 valence electron each. And then we have nitrogen, which will be 1 nitrogen, and that has 5 valence electrons for a total of 8 valence electrons. Now, you're not always going to get 8, but these were ones that are going to be similar to each other. That's why we're looking at them, water, and ammonia, and methane eventually. And so here we have now a central atom and the surrounding atoms. And as you get better at this, you'll be able to figure out which is the central and which is the surrounding atoms a lot more quickly. But for now, I'm going to draw in the Lewis diagram for each of these atoms. Right? Nitrogen has 5 valence electrons, meaning it has 3 unpaired electrons, and of course hydrogen has 1 valence electron. So we can put our nitrogen in the middle and surround it with our hydrogens. Then we go to our rule about drawing bonds. So we draw 1, 2, 3 bonds, 1 from each of the hydrogens to the nitrogen. And so, of course, that means there are 6 bonding electrons because there are 3 bonds. Okay, and so we subtract off 6 bonding electrons, and that leaves us with 2 valence electrons remaining. And so we come over here. Each of our hydrogens has a duet. It already has 2 because it has a bond to it. And so we put that remaining pair of electrons on the nitrogen. Okay. Now, the other thing we're going to do here is we want to check to make sure. And so I didn't do this on the first one because it was pretty well given, but you can see that nitrogen has 2, right? So each 3 bonds, so 2, 4, 6, and a lone pair gives us 8 electrons around it. So it has an octet. If we want to calculate the formal charges, right, we've got hydrogen. Well, each hydrogen will have 1 valence electron in the free atom, minus 0 lone pair electrons, minus 1/2 of the 2 electrons that are shared in the bond. So 0. And nitrogen, which normally has 5 valence electrons in the free atom, you'll subtract off the lone pair electrons. So there's 1 lone pair, meaning there are 2 lone pair electrons. So we'll subtract off 2 and subtract off 1/2 of the 6 shared electrons, right? 2, 4, 6 electrons. There are 6 electrons that are being shared. So 5 minus 2 minus 1/2 of 6 is also 0. Okay. So those are some pretty straightforward, pretty simple structures. And again, if you go through these rules each time, you'll be in pretty good shape to get the right Lewis structure, or very close to the right Lewis structure each time, okay? So before we get into some more practice, and you can see there are going to be some more practice molecules in here, there are exceptions to the octet rule. Most of the time we're going to use the octet rule, but there are exceptions. The first set of exceptions, okay, is incomplete octets. So what we have here is the element, so hydrogen, helium, beryllium, boron. Helium really is one of those ones that really is only atomic, right? You're not going to have molecules with helium. Beryllium will want 4. Boron will want 6 electrons, right? So these are the electrons that it wants. Okay, so beryllium wants 4 electrons, boron wants 6 electrons, and aluminum wants 6 electrons. Okay, those are ones that have, again, incomplete octets, right? In other words, not actually an octet, right? A duet, or maybe a quartet, or a hextet. Those are incomplete. They won't fill all of the surrounding, or the orbitals, with electrons, essentially. Okay. And the reason is they just don't have enough electrons around them, right? If you look at beryllium, well, so we can look at hydrogen first, right? Hydrogen's got 1 electron, so it's only going to form 1 bond, which means it's going to share, have 2 electrons that are shared. Beryllium, 1, 2 electrons around it, so it'll form 2 bonds, meaning it'll share a total of 4 electrons. Boron, 1, 2, 3, so it'll form 3 bonds, meaning it'll be surrounded by 6 electrons. And that will change later on when you get into 102 and you start looking at a certain type of bonding called coordinate covalent bonding, but for now we're going to stick with this. Then we have aluminum, which also has 1, 2, 3 valence electrons. So that's sort of the key here, is we have the number of valence electrons is going to dictate whether it'll have its octet or not in many, many cases, okay? The other sort of most common thing you're going to see is what are called expanded octets. So basically, when you have the central atom is in period 3 of the periodic table and below, you can have now more than 8 electrons surrounding it. So you can have an expanded octet, more than 8. Now the reason is that those are larger atoms. And if you have larger atoms, you can fit more electrons around them. Okay. So things like chlorine can be a central atom that can have more than 8 electrons around it. Now, it's still most of those types of compounds, sulfur compounds, phosphorus compounds, things that are in period 3 or below, they'll still tend to make compounds that have octets, but occasionally they will make compounds that have many more electrons than 8, okay? Now, the other class here of compounds are what are called free radicals, okay? So free radicals are things that you'll encounter a lot more in an organic chemistry class, but we need to know that they're going to exist. Now, these are going to be things that have with 1 or more unpaired electrons in the chemical formula. Essentially, when you add up the valence electrons, the total number of valence electrons will be an odd number. And generally, you'll see this a lot with the nitrogen atom in certain types of compounds, okay? The nitrogen atom will tend to form that because it has 5 valence electrons, and depending upon what it's bonded to, for example, in like nitrogen-oxygen compounds, it'll have an unpaired electron in many cases, okay? So those are exceptions that as you're making Lewis structures, you can look at those exceptions as being things that you'll encounter occasionally, so it's good to know those things. Okay. So let's look at some examples of those exceptions. Beryllium difluoride. So BeF2. Be has 1, 2 valence electrons. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. Okay, and so when we add them up, beryllium, 2 valence electrons, fluorine has 2 times 7 valence electrons for a total of, well, 2 plus 14 is 16 valence electrons. Our central atom is, of course, the beryllium because it's got more unpaired electrons in its Lewis diagram. So we have our beryllium and our fluorines. Okay, once we have the berylliums and the fluorines, we're going to draw bonds. And so that's 4 bonding electrons from the 2 bonds, so minus 4 bonding electrons, leaves you with 12 valence electrons to place. Now on these, we're going to place these electrons as lone pairs beginning with the more electronegative element. Generally, that more electronegative element is the one on the outside. Okay, it's the surrounding atom in many cases, except for when hydrogen's involved. So we're going to start placing electrons. Fluorine here has 2 electrons associated with it, so we can place up to 6 more electrons around fluorine to get its octet complete. So 2, so there's 1, 2, 3, 4, 5, 6 valence electrons placed, gives that fluorine an octet. We go to the next one to place the next 6. 1, 2, 3, 4, 5, 6. Now that fluorine molecule has an octet. We've used up the 12 remaining valence electrons and we're good. And so here we could do formal charges. Okay, so for beryllium, it would have 2 valence electrons in the free atom, minus 0 electrons in lone pairs, minus 1/2 of the 4 bonding electrons, or 4 shared electrons. So that'll be 0. And for fluorine, we'll have 7 valence electrons on each of them, minus there are 6 lone pair electrons, because each of them has 3 lone pairs, minus 1/2 of the 2 shared electrons in the bond, right? Remember, we're taking each of these fluorines one at a time to do this formal charge, okay? So it'll give us a total of 0 when we do that math. So these formal charges are good. We don't have to do anything with them. And finally, we'll do one more example and then we'll end for the day, this SF6. So sulfur is right below oxygen. It winds up having 1, 2, 3, 4, 5, 6 valence electrons. Fluorine, we know, has 7. 1, 2, 3, 4, 5, 6, 7. So when we do this now, we say, okay, well, I've got my sulfur, 6 valence electrons. My fluorine, well, this is SF6, so I've got 6 times 7 valence electrons. Well, 6 times 7 is 42, plus 6 gives us 48 valence electrons, okay? The sulfur goes in the middle, but you'll notice there are 6 of these. So now we're not limited to just the 4 sides. We're just going to space these fluorine atoms around the sulfur as best we can. Okay, so they're placed now, and we draw a bond between each fluorine and the sulfur. 1, 2, 3, 4, 5, 6 bonds now. And so those 6 bonds account for 12 valence electrons. So we subtract off 12 bonding electrons, okay? And we're left with 36 valence electrons remaining. And we're going to start placing those as lone pairs around the fluorine atom. So 1, 2, 3, 4, 5, 6. Remember, once we have those 6 valence electrons added, those 6 plus the 2 in the bond give us an octet. 1, 2, 3, 4, 5, 6. There's 12 of the electrons used up. 1, 2, 3, 4, 5, 6. There's 18 of the 36 electrons used up. 1, 2, 3, 4, 5, 6. There's 24 of the electrons used up. 1, 2, 3, 4, 5, 6. 30 of the electrons used up and 6 to go. 1, 2, 3, 4, 5, 6. We've now placed all of our electrons, okay? Formal charge-wise, so first off, all of the atoms except for sulfur have an octet. Sulfur has an expanded octet, which it can have because it's period 3 or below. So for formal charges, okay, we've got our sulfur. Do the middle atom first in this case. Sulfur in its free state, just by itself, would have 6 valence electrons, minus there are 0 lone pair electrons on sulfur, so minus 1/2. Well, there are 6 bonds which account for 12 shared electrons. So 6 minus half of 12 is equal to 0. So there's a formal charge of 0 on sulfur. Fluorine. Each fluorine, you would take them separately, but they're all equivalent. They all look the same. They all have 1 bond and 6 lone pair electrons. So 7 minus 6 minus 1/2 of 2 gives you a total of 0. So the formal charges here are also 0. Now, the reason that we're stuck with, we have stuck with formal charges of 0 today is because we'll get more familiar with this a little bit more tomorrow. We'll do a little bit of work with these tomorrow and get a little bit more familiar with these as we move through doing Lewis structures. And then we'll start to see formal charges that are non-zero, and we'll start to deal with some other things as we end or get closer and closer to the end of chapter 8. Okay, but for today, we've got some examples of doing Lewis structures. We've done some bond energy work and predicting energies of reactions. We've talked about the range of electronegativity differences and the partial ionic character of covalent bonds. And we're going to kind of continue with that tomorrow and on Monday as we move through chapter 8. Okay, and with that, I'm going to stop our recording and